Hi everybody, it's Elijah here. Today we're going to be going over a Navier-Stokes equation example for towards the end of chapter 6 in our fluid mechanics class. And usually, right, we do these examples on the whiteboard, but since we had kind of a rare occasion and had an online lecture, we're going to do a recorded example here. And I thought it would be more interactive if I wrote the problem on paper and did it for you live rather than just having the solution and going through it on my screen here. And I do plan on just putting the example part at the end of the lecture where I do the screen recording, but I guess I will just kind of read the problem here as well. That way, if you're just watching this video by itself, you're still going to understand. Alrighty, let's get right into it. So the velocity of a fluid particle moving along a horizontal streamline that coincides with the x-axis in a plane, two-dimensional incompressible flow field, was experimentally found to be described by the equation u is equal to x squared. Along the streamline, determine an expression for a, the rate of change of nu is your velocity in the y direction, component of a velocity with respect to y, part B, the acceleration of the particle, and part C, the pressure gradient in the x direction. The fluid is Newtonian. And sorry for the quality, I don't really have a fancy iPad or anything, so I'm just using my own personal camera and making do with what we can here. So, all right, I worked ahead and graphed this vector field for you using this GeoGebra website, just citing the source I used. So once you kind of get both of your velocity equations for the x and y direction, I worked ahead, I said right, but I wanted to give you a graph and visual here so you understand the problem better. So here you can see along the x-axis, right, the fluid flow is just in the x direction. There is no y component there. And that's what it kind of means when it coincides in the x-axis when we were reading the problem earlier. So if you were to basically have your x and y velocity functions and you pick points to graph, this is what your fluid flow will look like for this problem. Okay. And if we go to the next slide here, here is our very important Navier-Stokes equation. I just put this here because this is what we're going to be using for this problem. And I hope you enjoyed the lecture I presented on this. Right? You could potentially win $1 million one day if you solve mathematically how smooth curves work on the Navier-Stokes equation, because that's a millennium problem. But I guess we can get to this problem first, right? Before you solve your $1 million problem. So we will only be needing the x and y direction since we are working in the 2D plane, so we can ignore the z direction. Here is our Navier-Stokes equation condensed here and boxed in red. And I highly recommend, if you kind of didn't understand this, how I explained it, maybe rewatching it or reading about it. This is me breaking down the Navier-Stokes equation, right, in a nutshell. It's just your conservation of mass, which is just your del operator dotted with the velocity vector equal to 0. And right, this is just your partial derivative with respect to x, y, and z, dotted with your velocity vector in x, y, and z equal to 0. And in your Navier-Stokes equation, that's actually right here, but if it's equal to 0, this actually goes away. And I already talked about this in the recorded lecture, so I'm not going to go over it again, but this is essentially just your Newton's second law, right? So over here, if you apply conservation of mass and this term is equal to 0, this is going to be your mass, right, acceleration, and your sum of forces. And in this case, our mass is kind of like our density because we're looking at a fluid. And that is going to be, right, mass divided by the volume. So, okay. And the reason why I also bring this up is because we're going to be using, right, both of these equations to solve this problem. Right, and it's essentially these two equations. Okay, let's get right into the problem. put the problem right in front of me so I can see. Okay, so let's get started. Let's keep doing our good practice of doing our given, finds, assumes, and solution. Kind of like how our nice professors taught us before in previous classes, right? So here the given, right? I kind of made this sketch in the X and Y direction here. This is what I would envision the problem to be if there wasn't that fancy graph that I showed you on the screen there. Since we said that the velocity in the X direction coincides in the X axis, so this would technically be in the X axis, these arrows here. But I kind of just drew it over so you can see. Right, so U is equal to X squared. Our velocity of fluid particle along X axis. Assumption, incompressible flow field, right? Incompressible fluid just means density is constant. Newtonian fluid, right? That just means, if you remember in the first two lectures, I showed you a graph that was linear, that a linear relationship between the viscosity and the shear stress applied to a fluid. So that's essentially what Newtonian fluid is, and you can go back to the first two lectures if you need a review on that. So we want to find nu, right, which is your velocity in the y direction with respect to y. We want to find acceleration of the particle, and we want to find the pressure gradient, which is essentially just your partial derivative with respect to x. Okay, so let's get started. We can do part A here. And right, so this is why we do the given finds and assumes, because we want to work backwards. So we want to see, oh, where can we find this new derivative with respect to y? That's in our continuity equation, right here, right? You can also call it your conservation of mass equation, right? So, and I guess not to get confused, right? Your continuity equation we refer to as Q equals AV. It's also similar, right, conceptually to conservation of mass. But I guess I'll start calling this conservation of mass equation. So let's get right into it, right? So we have partial derivative of u, right, with respect to x plus partial derivative of nu with respect to y is equal to 0. Right, technically you can have your plus partial derivative of w with respect to z, but we are in a 2D plane when the xy plane. So we will not be needing it. Okay, so u is equal to x squared, right? That was given in the problem. And now we just want to solve for this guy right here, right? Because that's what part A is asking for. Make sure that we can see what I'm writing here. So let's move this term over to that side so we can solve for it. So okay, just move this term onto the other side. And now we can take the derivative of u with respect to x, which is just 2x, but there's a negative. So this is negative 2x. And we can actually rewrite this so we can see better. So that's technically your part A right there, already done. But since we're already here, right, we've been doing this a lot in class, we can solve for nu here so we can have this equation. So if I have partial of nu is equal to negative 2x partial of y, right? I can now technically integrate this on both sides. Let's go to the right here so we can save some space. So now we have nu is equal to negative 2xy, and then our constant is going to be a function with respect to x, right? Because we're integrating multivariables. So we took the integral with respect to y. So that means our quote-unquote constant, right? This is kind of like our plus c is going to be with respect to x. So, right, but we had the assumption, since the x-axis is a streamline, nu equals 0 along this axis. So that means, since we had this assumption that we're taking the velocity along the x-axis here, right? There is, here, let me just write it out here. So nu is equal to 0 along the axis. Right, so since that's 0, you can just assume, right, that this f of x is equal to 0. Okay, so just for this problem, because right, nu equals 0, because there's no y component here. Okay, so nu is equal to negative 2xy. Okay, so now we're moving on to our part B, right? And let's remind ourselves, what are we solving for part B? Part B is the acceleration of the particle. Okay, so acceleration, I am now gonna pull back up our Navier-Stokes equation here. So I am gonna just quickly write this out now. So in the x direction, right, the Navier-Stokes is rho partial u partial t plus u partial u partial u partial x plus nu partial u partial y. And this was just from the slide I previously showed. You know what? Let's make this easier for us to write and not include the z direction. We're going to assume that goes to 0 because there's no z direction. Okay. So a lot quicker to write on here than writing on the board. Okay, ignore the z term there. This is just from your slides, except there is no z term. Okay, and then we'll write the y. And lucky for you, you can actually just skip this. So if you're watching this video, you can just skip through this part. Okay. Okay. Sorry, trying to get a good angle here. We just essentially copied and pasted from our slides, right? And I'm going to double check that this is right so we don't have any mistakes later on. Okay, that looks good to me. So now that we have this written, right, we want to get our acceleration, right? So in the Navier-Stokes equation, where's our acceleration? So like I said, this right-hand side here, that's mainly for our forces summed up, right? And our acceleration, right, this is m equals a, it's basically these terms right here. So I'm going to extract, so we can write here, acceleration in the x direction, right? It's going to be equal to just this. And here, since it's incompressible fluid, density actually will not matter as much. Should not be changing, but we're still going to be given a value for it. So let us get this value here. So u partial x plus. Okay, so that's our acceleration in the x direction. And then let's get our acceleration in the y direction too. So it's going to be okay. I think that looks good. So now let's just solve. So u, what is our u? U is x squared, right? So that's going to be x squared. This is u with respect to x, x squared plus 2 times 2x plus nu, negative 2xy, negative 2xy. And then this is going to be u with respect to y, which is 0. Right, we do the math here. This is just 2x cubed. So I like to kind of rewrite here. That way we know. Okay, so let's continue. U, right, we have as x squared still. We have nu with respect to the x, so that's going to be negative 2y. Okay, plus nu here. And then nu with respect to this, just negative 2x. Yep. And then this is going to be so this is going to be 2x squared y. Right? Yeah. Okay. But remember, along the x-axis, y is equal to 0. So technically, right, ay is actually equal to 0 here, because if you plug in 0 here, you get 0. The reasoning for that, right, is because we are only going along the x direction, which I previously explained in the problem. So, in short, your acceleration is equal to 2x cubed just in the x direction. Just like that. Okay, so let's check off. We got A, we got B. Now we have to find C, pressure gradient with respect to x, right? So partial derivative of pressure with respect to x. And let's look around here, right? Where can I find that? So we go back to our Navier-Stokes equation, and that is right there. Okay? So let's solve for that. I guess we can kind of already see, but there's no gravity in the x direction, right? Because we usually only assume that in the vertical direction. And if this comes up in an exam or anything, you can ask me, or I can state that in there. And the reason why I'm putting that is, right, this is going to cancel out. Okay. So, okay, make sure we're still recording okay. Okay, nice. So, now, since that's canceled out, we still have this term over here, right? And then we have this term over here. And then we have our acceleration term over here. Okay, so we essentially have rho equal to u partial u over partial x plus nu, which is partial u over partial y equal, let's just call this whole term acceleration. It'll be easier, right? Rho times acceleration. That way I don't have to rewrite it over and over. So rho acceleration in the x is equal to negative rho times taking the derivative of pressure, partial derivative pressure with respect to x. This is 0, so that will go to 0 plus mu x squared plus okay, and we can get x alone, right? Our acceleration by itself. So negative 1 over rho here, partial p over partial x plus we have mu over rho. Just rewriting that. Okay, and what is a? We have it here, right? 2x cubed. So we have a, plug that in there. Rewrite everything once again. And I think you kind of see where I'm going here. So much writing, my pencil is not holding up. Okay, so now we're going to just do some algebra and solve for this guy right here. So I can let you do the algebra, right? Because we have let's not get messy here. This is looking like a 2. That's partial derivative twice. So once you solve everything, right, you have your u, you can derive that twice. You have your u, you can derive that twice. Leave mu as mu, leave rho as rho. You have your, this is the term you're isolating, right? So you're going to move this term to that side, multiply by density on that side. And your final answer, I'll let you do this algebra here on your own because I'm running out of room. You just isolate it, right, and do algebra. You'll have your answer as okay, and after some algebra and some differentiating, you just follow those, right? And that's why it's really important to understand how these are read. Okay, and I explained that already, right? You take the derivative of this function with respect to the variable at the bottom. If there's a 2 on there, you do it twice. So just get used to the notation, but you should already know that because you took all the calc classes and diff EQ classes. So, okay, so now this is our final answer of our pressure gradient with respect to x. So, right, in summary, we found our derivative of nu with respect to y, or its rate of change, which is this function right here. We found the acceleration of the particle, which is right here. And then we found the pressure gradient, which is right here. And right, this all came from our favorite Navier-Stokes equation, right? So it comes from the conservation of mass, and right, these equations are the actual Navier-Stokes equation itself. And the main takeaway from this problem is, right, you can ask questions, what are these values out of these equations? And you can basically model, kind of any fluid, and you can get those values. Maybe you're working at work and, oh, I need the acceleration for my fluid. Oh, I need the velocity, right? Oh, I need the pressure difference in the x direction. So that kind of shows how you use the Navier-Stokes equation with the conservation of mass equation to find these values. And all right, that is kind of everything. We're kind of getting close to 30 minutes here for this example, but right, feel free to skip through it once there's a lot of writing of partial derivatives there. So it's just me double checking work. So, okay, I'm going to wrap up this problem. If you have any questions, feel free to email me. And like I said, I'm going to try to link this video towards the end of the video lecture so they're connected. All right, thanks everyone for watching and bearing with me. And I will see you all in class soon again. All right, bye-bye.